Welcome. On this video, we're going to take a look at integration using use substitution. We're going to take a look at one indefinite integral and a one definite integral. So let's get started. Let's start by taking a look at example number one. And under example number one, what we want to do here is we want to perform this indefinite integration. Now we want to use use substitution. And when you have an integration and there is some kind of a square root involved, most of the time we're just going to let our inside of a square root be equivalent to that variable of u. So let's start with that. Let's let u equals 2 minus x. So now that we have that, remember that we want to change the variable of the whole integration. Let's try to rewrite everything in terms of u. So far, we know the following. We know that the inside can be written as u. So now we're going to get times u to the 1/2. But notice that we have two big problems. And the first big problem that we encounter is that the derivative, it is still in terms of x. And we still have this x involved here. We want to make sure that everything is written in terms of u. So let's take care of that derivative. Let's try to see how can we write that derivative in terms of variable of u. So the way that we're going to do that is as follow. We're going to take a look at our u variable that we do have right here on the right hand side. And we're going to take the derivative on the left and we're going to take the derivative on the right. If we take the derivative on the left hand side, we're going to get du dx. And notice that we're taking the derivative in terms of x. The derivative of 2 is just 0, which we're not going to write. And the derivative of negative x is negative 1. Again, remember that we're trying to write dx in terms of du. So on the right hand side, let me put it over 1. And if I perform cross multiplication, I'm going to get du times 1 equals negative 1 times dx. And if we solve for x, dx, we're going to get dx is equal to negative du. Let's rewrite our integration with that new information. So now we're going to get x plus 1 times u to the 1/2. But now notice du, now I can rewrite it as negative du. I'm sorry, dx, now we can write as negative du. And I think things are looking better because now notice that, fine, I have a variable of u and now my derivative is in terms of u. The only thing that we need to fix now is this variable of x, because the whole integration, we need to write it within the same variable, the variable of u. So how can we write x in terms of u? Well, don't forget about how we define u. We said that u is equals to 2 minus x. Well, we can manipulate this expression. So let me just rewrite it here. 2 minus x. And let's solve for x. And look at what's going to happen when we do that. Take away 2, so we're going to get u minus 2 equals negative x. So therefore, x is equal to 2 minus x. I'm sorry, 2 minus u, not 2 minus x. And look at what we have accomplished. What we have accomplished here is that now we know what is the representation of the x variable in terms of u. So what we're going to be doing now is we're going to come back to this. We're going to come back to our integration. And now we're going to substitute x with the expression of 2 minus u. And let's see how is that going to help us. So now we have integration 2 minus u plus 1 times still u to the 1/2. And now this negative dx, I'm going to pull the negative to the front and I'm going to leave du there. So let me bring the negative to the front. And now we got du. And let's stop here for a second. Well, let's not stop there yet. We can still simplify the inside of that parenthesis. That can become 3 minus u times u to the 1/2 du. Now let's stop here for a second. Look at what we have accomplished. We have rewritten the problem. But now the benefit of that is that notice that everything is in terms of u. The derivatives in terms of u, and all the variables are in terms of u. And this is exactly what we want to accomplish when we want to perform use substitution. We want to rewrite the whole problem into a new variable, and that's what we have just done. We started with an integration using the variable of x, and now notice that we have rewritten the problem all in terms of u. The only thing that we need to do here now is try to rewrite it as some kind of a polynomial. And the way that we're going to accomplish that is, well, let me just erase this. We still need to distribute this u to the 1/2. So let's distribute, because remember, it is being multiplied. So what happens when we distribute? Well, we still get this negative outside. So now we're going to get 3u to the 1/2 minus u 3/2 du. And the way that we're getting this 3/2 is, just to remind you, u times u to the 1/2. Well, they have the same base, so we can add the exponents. 2 over 2 plus 1 over 2, which is u 3/2. And that's how we are obtaining this exponent here. This is good. This is nice, because now notice that the whole problem is written as a polynomial. The whole problem is written in terms of u's and even the derivative. Now that we have it in this form, now we can perform our rules of integration. So notice that here I have two terms. I have the term 3u to the 1/2 and negative u to the 3/2. Remember that when you have different polynomials, what we can do, we can just take the integration one term at a time. So I'm still going to leave that negative in the front. And now I can say, well, my first term, my integration is going to look as follows. Pull the 3 out, take the derivative of the variable, and then minus, notice that here I'm forgetting du, because du has to be present in every single term, minus integration u 3/2 du. And now let's take care of the integration one term at a time. So we got that negative in there, 3, the integration of u to the 1/2. Remember that we add 1 to the exponent, and we do the same on the bottom. So we're going to get u 1/2 plus 1 over 1/2 plus 1. That takes care of my first integration, or my first term. This integration is equivalent to this, minus u 3/2 plus 1. Do the same for the bottom, 3/2 plus 1. This integration that we have here is the integration that we would obtain with this expression here. And don't forget, since we have an indefinite integral, we need to do a plus c at the end. Now let's try to rewrite this. Let's try to make it a little bit more simple. So we're still going to get 3. Now 1/2 plus 1, that's 3/4. I'm sorry, 3/2. Denominator, still 3/2. Minus 3/2 plus 1, well, that's equivalent to 5/2 divided by 5/2, still plus c. Now, here is what it's interesting. Remember that any time that you are dividing by some kind of a fraction, that is equivalent to just multiply by the reciprocal of the denominator. So let's complete our problem right here on the right-hand side. Let's continue it up here. We got negative. And now we got 3 times the reciprocal of the denominator, u 3/2, minus reciprocal of the denominator, u 5/2 plus c. And let's just polish this a little bit. Notice that now here the 3's are going to cancel out. So we got a negative still on the outside, and now we got u 2u 3/2 minus 2/5 u 5/2 plus c. And there are still two things that we need to perform. The first one is we need to still take care of this negative. So let's do that. If we distribute that negative, now my first term is going to be negative 2u 3/2 plus 2/5 u 5/2 plus, or we can call it negative c if you may. And at this point, when it comes to integration, we are done. But we have to remember where we come from. We came from an integration that was written in terms of x's. So our last step, we have a final result, but notice that this final result, it is still in terms of u. So the last thing that we want to do here is remember what u stand for. u was a placeholder for the expression 2 minus x. So therefore, on our final result, every time we see a u, we're going to replace it with 2 minus x. 3 halves plus 2 fifths, 2 minus x, 3 halves minus c. And here we have our result. Let's recap what we just did here. We had an example, or we have an integration. We acknowledged that there was a big problem. And the problem is that the expression was, a little bit intimidating. So what we did is this. We rewrote the whole problem. We started by letting the inside be equivalent to u. We put it right here on the right-hand side. And then we acknowledged that the whole problem needs to be written. So the next thing that I tackled was this dx. Took the derivative on the left, took the derivative on the right. Now I have an expression of dx in terms of the u. Plug that in. And then we acknowledge that we still have that x. That was a problem here. So the way that we tackle that is we went back to our substitution and we rewrote x in terms of u. Now, we discover that u was equivalent to 2 minus u. So all we did at that point, we plug it in, we simplify, we got it into a very simple form, and now that we have our integration in terms of u, we apply our rule of integration. Take the integral of a variable with an exponent, add 1 to the numerator, and do the same to the denominator. We simplify, we simplify, we simplify. We got an expression at the end here. But remember that this expression was in terms of u, but our original was in terms of x. So the last thing that we did, we got our x again. We got our u. We remember that u was a placeholder for the expression 2 minus x, so we just plug it back in. Now, it is okay for us to write it in this form, or we could also have written it in this form. Because remember what does C stand for? C is just a parameter that we use to represent a placeholder for a constant. So if you are subtracting a constant or you are adding a constant, you're still talking about a constant. But some books decided to just leave it as minus c. Some books define it just as plus c1. But you gotta define what c1 was. C1, it's a parameter that we are using for c. So whichever of these two forms, they're okay as our final result. So this is one quick example whenever we have a indefinite integral. But now let's see how things change whenever we are talking about a definite integral. And remember that the reason why we call it a definite integral here is because we actually have some limits of integration. We want to find the integral from 0 to 2, where on the first example, notice that it was just a simple integral. We never set up what were our limits of integration. So that's the difference between an indefinite and a definite. Indefinite, there is no limits of integration, and that's why we need to write our expression with the plus c. Definite, we do. So by introducing these limits of integration, how is our process going to be different? But the main idea is still the same. If I take a look at how my integral is written, I can see that it's fairly challenging. Is there a way to make my life a little bit easier? And there's the way. The way that we're going to tackle that is by introducing this so-called variable u. And again, let's let u represent the inside of the square root. It seems like that's going to make our life a lot easier. If we do that, let's rewrite our our integration. Our integration is still from 0 to 2, x on the numerator, but now notice that we're going to have u to the 1/2. Again, 1/2 is the exponential representation of the square root, the x. We still have two big problems to solve, or to take care of, I should say. I still need to rewrite the x in terms of u, aka we need to find out what du is, and we need to take care of this x. Everything has to be written in terms of u. Let's take care of this problem. Let's take care of rewriting the x in terms of du. So let's go back to our definition. If we are claiming that u is equals to 1 plus 2x squared, let's take the derivative on the left and the right in terms of u, in terms of x. So the derivative of u in terms of x is du dx. The derivative of 1 in terms of x, well, that's 0, which we're not going to write it. And the derivative of 2x squared, that's 4x. Now, let's put it over 1. If we perform cross multiplication, we're going to get du times 1 is equal to 4x times dx. And if we solve for the dx, we can see that dx is going to be equivalent to du over 4x. Let's, hold on, I think I did something wrong here. Oh, no, everything is fine. So let's go back to our problem and let's substitute that. Integration from 0 to 2, x, u to the 1/2. But now, instead of dx, we can write it out as du over 4x. Let's pause here for a second. In this case, we don't have to find out what's the value of x in terms of u, because when we plug in this expression of dx, now we know that dx is equivalent to du over 4x. Notice that by doing that, the problem is set up in such a nice way that now these x's are going to cancel out. These x's are going to cancel out, and now we're going to get the following. From 0 to 2, 1 over u to the 1/2 du over 4. But remember that everything is being multiplied, so this 4 that we do have on the denominator, I'm going to pull it in front of the integral as 1/4. So now, if we rewrite it, sorry about that, we're going to get 1/4 integration from 0 to 2. But this expression, let me just, instead of calling it 1 over u to the 1/2, let me pull it to the front, not to the front, sorry. Let me put it to the top, which is going to change the sign of my exponential. 1/2 du. And let's stop here for a second. Let's acknowledge what we have just done. What we have just done is this. We had an integration, everything was in terms of in terms of x. And what we just did here, we rewrote the same integration, but now in terms of u. We got du, and now the variable is u. And this expression that we do see here, I can see that it's going to be way easier to find the integration of compared to the one that we just started here. But before we perform the integration, we have to acknowledge one thing. The limits of integration. If we go back to the original problem, notice that these limits of integration, the values of 0 and 2, both of them, they were given in terms of x. The original problem was given to us in terms of dx. That's a conflict because now we just rewrote the problem in terms of du. So these limits of integration, we cannot use those limits of integration because those limits of integration were in terms of x's. We're not working with x's anymore. We're working with u's. So what we're going to do now is we need to find the equivalency of those limits of integration, but in terms of u. And the way that we're going to accomplish is as follows. Let's figure out what is my new upper limit of integration. So upper limit of integration. We're going to take a look at the definition that we did for u. We establish that u is equal to 1 plus 2x squared. So what is going to be my value of u when I let x be equivalent to 2? Because remember, this 2 is my upper limit, but I want to see what is the u equivalency of when I plug it into my definition here. So if we do that, let's plug it into that expression right there. So we're going to get u equals 1 plus 2 to the second, which can be simplified as 1 over 2 to the fourth, which is just 9. So now that is my new limit of integration in terms of u. So let's just reflect that on our problem. So now we're going to get 1/4, but now my new limit of integration, or I shouldn't call it new, but my limit of integration in terms of u is not 2 anymore. It is now represented as 9 in terms of u. And we're going to do the same for the bottom. Let's call this the lower limit of integration. We're going to do the same. We're going to take a look at the substitution for u, but now let's plug in what is the equivalency whenever x is equals to 0. So now we're going to get 1 plus 2, 0 squared, which we can see that that's just going to be equivalent to 1. So now that implies that my lower limit of integration in terms of u, it's equivalent to 1. Let me rewrite the whole problem, or what is left here, u to the negative 1 half du. And let's acknowledge what we have done here. We rewrote the whole integration, but now in terms of a simple variable of u. And then we acknowledge that my limits of integration were still in terms of x's. I need to find the equivalency form in terms of u. So what we did, we went back to our definition of u, and we plug in those values. We plug in 2 for x, and then we saw what was the outcome. The outcome was 9, so that implies that my upper limit integration in terms of u, it is equivalent to 9. And then we did the same for the lower limit integration, but for that we plug in the value of 0. And now this, what we have here, this is the integral of the original problem, all in terms of u. Derivative in terms of u, variables in terms of u, and limit of integration in terms of u. Now that everything is in order, now we can take care of the integral. So let's take care of the integral. So we're going to get, still, let's leave that 1/4 outside. And now let's perform our limit of integration. Again, remember that what we do here, we add 1 to the top, we add 1 to the bottom. But in this case, we're not going to do plus e because we're talking about defined limit of integration. So due to the fundamental theorem of calculus, we're going to evaluate the upper value minus the lower value. And now let's take care of that evaluation. If we simplify, on the numerator, we're going to get u to the 1 half. On the denominator, we're going to get 1 half one more time. And notice that I want to simplify this as much as possible before I perform the substitution. Remember, if we are dividing by 1 half, that's the same as multiplying by the reciprocal, where the reciprocal is just 2. So we're going to get 2 u to the 1 half, 9 over 1. And if we simplify that, 1/4 times 2, that's going to be 1 half, u to the 1 half, 9 over 1. And let's stop right here. Because a big misconception from students is that you want to plug x back. Like now you want to plug this u, you want to plug this x into that expression again. We don't need to do that anymore because we are talking about the limits of integration in terms of u. So there is no need for us to plug back that x. If you wish to plug back that x, then you have to use the old limits of integration, 0 and 2. But since we are evaluating on the limits of integration in terms of u, then there is no need for us to plug the x back. So now that we have it in this form, really what it is we're just going to be applying the fundamental theorem of calculus, which says evaluate the expression at the upper value, which is 9, and then subtract the evaluation of the lower value. And now at this point, it's just a matter of finding out what that is. So we're going to get 1 half, the square root of 9 is 3, minus 1 half, the square root of 1 is 1. So let's just finish this up. We're going to get 3 halves minus 1 half, which is going to give us 2 over 2, which is just going to give us a value of 1. And with this, it concludes our lesson, or just 2 quick examples when it comes to the integration of a definite and an indefinite integral, and they were both done using the technique of u substitution. I hope this helped.